So it's my pleasure to introduce the second speaker, who's also from CWA. So he worked in the past a bit on sped programs and still does, I guess. Also a bit on quantum query complexity Boolean functions. And today he'll tell us about some joint work with a former student of Frederic, among others. So Arjan, please take it away.
Yeah, thanks, Sander, for the kind introduction. I'm very happy to be here to give a talk about research that was on my mind for quite a long time during my PhD. I think, well, in total, I've been spending 1 or 1.5 years, but like on and off, like thinking about this topic. So I'm very happy to kind of, have also more in-depth discussions during this talk. So like if you have any questions, then feel free to interrupt. Yeah, to have a discussion. So yeah, so what I'm going to be talking about is quantum algorithms for multivariate mean estimation. And as usual, I think it's the best.
I had to press that. Do we even need the camera on the screen or not?
This means you need to shift back to the other.
So let me start by introducing the problem we're considering. So let's consider that we have a probability space given by some outcome set and a probability measure defined on this outcome set. And let's consider that we have a random variable defined on this probability space. And I'm a guy that always likes pictures. I made a little picture of what's going on. We have some kind of unstructured outcome set here. Each of the possible outcomes has like has the probability associated to it. And what the random variable does is nothing more than a function that maps every possible outcome into some vector from some bounded set B in d-dimensional real vector space. And now I'm sure we all know that the mean is or the expectation value is defined in this way. I'm sure we've all seen. And the mean estimation problem is the following. We want to find an approximation to this mean, and specifically we are interested in an approximation up to L infinity norm. So we want to really have like a little box around the true mean, and we want to find a vector somewhere in this box. Later on in this talk, I will also shed some light on what happens when you change this L infinity norm to some other norm, but for the time being, let's only consider the L infinity norm. Then for this problem, there's a couple of different variants that we will be considering. The first distinction we can make is whether like the dimension over vector space is this 1 or whether it's bigger than 1, the univariate or the multivariate. And also we will be considering whether we have like a classical or a quantum access model to this random variable. This I will define in the next slide. And for a long time it has been known how you can kind of estimate this mean up to an infinity error epsilon, classically in the univariate and multivariate case, and quantumly in the univariate case. But for a long time, it was kind of unclear how you would do this in the multivariate case when you have a quantum setting. And so this will be the topic of this talk, try to see if we can kind of combine the ideas for the univariate case in the quantum setting and the multivariate case in the classical setting, try to combine them such that we get a quantum algorithm in the multivariate setting. Okay, so I hope that kind of the problem itself is clear. So then let me formally define a little bit what I mean with these classical and quantum input models. Yeah, so just as a reminder, this is a problem we're considering. We want to approximate the mean. Now, classically, what we assume to be able to do is to like obtain samples from this outcome set. So we consider that we have like two different operations that we assume we have access to. One is to obtain a sample from this outcome set according to the probability distribution that is defined on it. And the other is to be able to, once we have such a sample, compute the corresponding vector in the d-dimensional vector space. So we assume to have access to these two operations. And when I say that we have quantum access, I want to find like the quantum analogs to these two operations. So the quantum analog to the first operation is the ability to be able to create a superposition over all of your outcomes in your outcome space, with the corresponding amplitude being the square of the square root of the probability.
Just a quick question about the classical access model. So you're assuming something stronger than the model where I just give you a random vector and you get samples like that.
So yes, I'm kind of splitting this up into two parts. You could always view already the omegas as being the vector itself, and then having this function being the identity function. Then you recover your model. Like there is some reason why it is like nice to split it up. I'll come back to this all the way in the end. Right. Yeah. So what we're after is kind of like finding the quantum analogs of these two things that we assume to have access to, and the quantum analog of kind of sampling from the outcome set is the ability to build a superposition over all possible outcomes weighted by the probability, defined by the probability distribution. And secondly, the computation of like the random variable is really like an operation that, given some outcome and some other like register that contains only zeros, writes a binary description of this random vector of this vector x of omega in like really in bits. So really taking a qubit and flipping it to 0, 1. Yeah. So you should really think of this x omega as really like writing all of the entries of your there. And so just a bit of terminology. Whenever I say that we use a certain number of quantum samples in our algorithm, what I mean is that we use applications of these operations. So one quantum sample means one operation of either of these operations that we generalize. So if we have an n quantum sample algorithm, we make n calls to these operations. Okay. Any questions?
Does it matter if there's like a garbage register in this?
Yeah. So you can always absorb the garbage in the definition of omega. So it doesn't matter. Okay. So
Of course, yeah, but then the point is x, then it has to be consistent with that garbage, right? So
sure. So then like your definition x will have to ignore whatever.
Yeah.
I mean you can put all these things in the definition.
Ignore in a nice way, right? Because otherwise you're entangled with that. Like it cannot live entanglement in some sense.
I mean it leaves the description of omega anyway.
Okay, I see. Okay.
And also you probably assume infinite precision or
Yeah. So this binary description will at some point have to be truncated. Okay, so let's maybe first have a look at like the simplest possible case, like the classical univariate case, and then try to see how we generalize from there. So in the classical case, what the idea is that we want to find like an epsilon approximation of this expectation value. And let's for the moment assume that our random variable takes only values in the interval 0, 1, right? So that's just really the simplest possible setting. Now I'm sure that like the classical algorithm in order to do this is something we've all seen before. You just take n samples from your random variable and then compute the average of this. And then what you can show is that this will approximate the expectation value up to 1 over square root. So if you want an epsilon approximation, you need 1 over epsilon squared. Spark some remembrance from. Yeah, so then the question is, how can you do this quantumly? Like is there something better you can do quantumly? And the answer is yes. And this is something that has been known for a long time, but let me still explain like how it works, because this will be like a useful building block in generalizing to multivariate. So how do we do it quantumly? Well, what we can do is we can start in like the all zero state. So we start just with like the memory being all zeros. The first thing we do is we kind of generate a superposition of all of our outcomes. And next, what we're going to be doing with this extra 0 is we're going to want to kind of make a rotation where the rotation that we do on this final qubit depends on where we are in this interval. So specifically, we want to be doing like the following operation. So given our outcome omega, we want to calculate what kind of this value x of omega is. And next, we want to do like a rotation on this final qubit such that we rotate like the say cat1 into it with like the amplitude square root of x. And for those of you that maybe haven't seen so many quantum algorithms, like before, I'm going to ask you to kind of assume that this is something you can implement once you have like a binary description of x form. Right, and then like you can compute this the description of x of omega, do this rotation, and then compute it relatively easily. Okay, then now if we look at this, we can kind of take this final cat1 out of the parentheses, and then kind of like group everything together. And now what you can see is that if you were to measure this last qubit, then the probability of getting 1 is exactly going to be the expectation value. Right. So in the end, we can kind of rewrite this whole expression. We can kind of group together like this, everything in front here, into like something that has norm square root of the expectation value of x. And so if we measure this last qubit, then the probability of getting 1 is going to be the expectation value. And now there's like a known result, which is called like amplitude estimation. This is a result from 2000 by okay, I would have to look exactly. Yeah, and so this result tells you that you can find an epsilon approximation of this probability in time 1 over epsilon. And now what's interesting to see is that, hey, here we are doing something in 1 over epsilon squared, and here we're doing something in 1 over epsilon. So that means that when our epsilon gets smaller, the quantum algorithm is going to be quicker than classical one. So we find the quadratic speed in the quantum set. So this is something that was known for a long time, and one of the reasons why people think that the quantum at some point can be because in the end, apparently it will give you an algorithm that's quicker. Okay, so that's the univariate case. Maybe now let's have a look at the multivariate case and see why it was so difficult for a long time to see how you could do this quantum. So the interesting thing about the multivariate case is that classically there's not a lot to change. There's not a lot that changes. So classically, let's now assume that we have a random variable that takes values in like a unit cube, and the classical algorithm that kind of evaluates your expectation value, it looks very similar to what we've seen before. So we kind of run the one-dimensional version, but now we just take n samples and we just compute the average, kind of like element-wise. And then it's not so easy to, or not so difficult to show that every element individually is going to be determined with high probability up to precision epsilon. So all we need to do is we need to kind of like run this a logarithmic number of times in order to kind of boost the success probability to something that's very close to 1. And then with a simple argument, you can show that kind of you can get it to work for all variables. So yeah, so this what I just described is called the median trick. Just run this like a logarithmic number of times and take the median fall out, like element. And then like you can show that the resulting approximation you get is going to be 1 over square root n in our infinity norm. And the total number of samples you're using is like logarithmic in d over the precision square. So somehow, like the classical algorithm is very similar to what we've seen in the univariate case. So that suggests that maybe we can also try to just take the quantum algorithm in the univariate case and try to make that multidimensional as well. So let's try to see what happens then. Like what we were doing in the univariate case in the quantum setting is that we were encoding this expectation value somehow as an amplitude in our quantum setting. But it's very much unclear what like an amplitude is whenever you want this thing to be multivariate. Like, it's not clear what that's supposed to mean. So this was kind of a roadblock for something like 15 years. Like that is somehow not clear what we want if we want to encode this expectation value as an amplitude. And so in the remainder of this talk, I will kind of be digressing and talking about what you can do in order to overcome this roadblock and what you can and cannot. So there's not an easy answer to this. So like I'll be delving a bit into the subtleties. Okay, clear so far? Any questions? Okay. Yeah, so then in order to be able to like say a bit more about what you can do in order to encode stuff in multivariate things, I'll have to do a little intermezzo, which is really a work from Gilyén in 2018, which really paved the way for kind of all of the things that I'm going to say after. And this technique is called Montanaro conversions, or at least that's how I refer to it. They don't give it an explicit name. Yeah, and so let's consider the setting where we have like a function that acts on a finite set and gives back values in the unit interval between 0 and 1. And let's try to think about how we can evaluate such a function on a quantum computer. And I'm going to list 3 different ways in which we can try and evaluate this function on a quantum. So the first thing is most similar to what you can do on a classical computer. Suppose that you have given your input in some register and you have like all zeros after. Then a binary oracle will write like a binary description of your function value in the extra register. And it will do so with some finite error because, as Fred already pointed out, sometimes you have these truncation things happen. Then there's also something that's called a probability oracle, which, given like your input in some register, will do one of these rotations that we already saw earlier, and will encode your function value in the probability. So if you were to measure this state, like if you were to measure the final qubit, you would find 1 with probability, the function value. And finally, there's something called a phase oracle, which, given the input state, given the input to your function in some state, will rotate the phase of this particular state over an angle that is the function value. So these are 3 different ways in which you can kind of like have an operation, do something based on what the function value is of the function that you're trying to do. So at this point, it's not clear like how you would build any of these, right? But I'm just like defining the operations, like defining what I mean with the words phase oracle, probability oracle, etc.
Can we implement probability oracle using binary, or like can we do these?
Exactly. So, the relevance of these things is that you can interconvert between these two. So if you have access to one, you can build access to another. And so there's like, so here I made a little graph which shows you like possible ways of converting. There are more connections, but I only drew the connections here that are kind of unconditional. For some of the connections, you need a little bit more like more extra information on your function, which, I mean, I don't want to dive into these sort of things at this point, but I just want to say that there's like more than meets the eye in this picture. But so
you will explain what the arrow means. So.
Yeah, so what was proved in this work from 2018 is how you can take a probability oracle and turn it into a phase oracle. And so I will not go into like how this conversion specifically works, because like it's a very technical result. Like this is something that goes down a couple of papers and like uses quite some advanced techniques. But the interesting thing here is that the overhead being incurred by converting from the probability oracle to a phase oracle is only polylogarithmic in the precision with which you want to do it. So if you want to do this conversion up to like some particular precision, you only have like a number of calls to this probability oracle that scales polylogarithmically in this precision.
So the reverse direction is trivial, or it doesn't exist? So
the reverse direction exists as long as your function outcomes are not in 0, 1, but are in delta and 1 minus delta. So you need to be bounded away from the endpoints of your domain. Then you can do the reverse direction too. Yeah, and then the complexity depends on how far, like how big a gap delta you have. Yeah, and it's also proven in the same paper. Any more questions? So yeah, so specifically this red arrow is what we will be using in the rest of this. Okay, so now what we can do is we can take this univariate quantum algorithm that I was talking about before, and try to rephrase it, but now with this oracle conversion ideas in mind. And like in the coming few slides, I will be doing this. So kind of like take the univariate case, phrase it in this quantum oracle conversion idea, and then give you an idea of how you then generalize things to the multivariate. So first, we're going to reconvene and look at the univariate case. So again, we're going to have like a random variable that maps values to like the interval 0, 1. And what I'm going to do next is I'm going to define something that I call a grid G, which is basically just a collection of points also in the interval 0, 1. And I hope none of you have this G, but I really mean that you kind of start at 0 and don't include 1. Yeah, so we define this grid G. And now we're going to define a function which takes points in this grid G. And the function is defined to be like this grid point multiplied by the expectation value of your random variable. And now the question is, okay, can we actually compute this function f? Can we build one of these oracles to one of the nodes in this graph on the previous slide in order to be able to quantumly compute this function f? Do know that we can build a probability oracle graph. And we can build it in a very similar way as what we saw in the univariate, in the original univariate algorithm. All we do is we add a couple of G's to all the expressions we had before. So we add like a register that contains like the specific grid point we're considering. And this G just carries over everywhere, and we multiply it whenever we build this rotation that depends on wherever in the interval we are. So now we don't rotate over like x of omega, but we rotate over G times x of omega. And in the end, this thing carries over all the way to the probability of measuring 1. And as you can see here, now we have computed this function value f in the probability. So we have built a probability oracle to this function f. And now we can use this result from András and others to take this probability oracle and turn it into a phase oracle. So we can now build this operation with like polynomialistic overhead to compute this function f in the phase. So rotate the phase over an angle g times e of x. Any questions about this? Okay. So now the question is, why is this useful? Well, this is useful because if you consider kind of the gradient of this function f, or like the derivative, because it's a one-dimensional one, and you can see that the derivative of this function is exactly like the thing we're after. The derivative is exactly the expectation value. And so what we can do is we can kind of like take the algorithm to kind of compute gradients, which is also from the same paper, from this 2018 paper, to kind of recover whatever this expectation value is. So I will explain next how this works. So this is what we borrowed from the last slide. We have this function definition, and we can implement its phase oracle. And recall that there is the following operation, which is the one operator. Okay, so maybe for those of you that haven't seen so much quantum, like this is really one of the most standard operations that you will find in any quantum textbook. It can be implemented in the circuit very easily. And so what the quantum phase transform does is it takes a computational basis state and like builds a superposition over all the points in the grid, and has some phase that depends linearly on the point in the grid where you are. And what we can now see is that we can build the following algorithm on your quantum computer to estimate this expectation value, which is the following thing. Start with a uniform superposition over all your points in the grid, and apply this phase oracle a number of times, let's say capital N times. And the resulting state that you will get is that based on your point in the grid where you are, you're going to get some phase in the amplitude of your state. And if you kind of see now, this expression here looks very much like whatever the quantum equation from gives you. So it should kind of give you the idea that if you now take this Poincaré form and apply it in reverse, then you should get something that estimates this expectation value. So let's do that. Let's apply like the Poincaré form in reverse. And then what you will find is that it will give you like a rounded version of something that depends on the expectation value. And it will round towards the nearest integer. So the higher we choose n, the bigger we are amplifying the expectation value with. So the less effect this rounding will have. So like the higher we choose n, the better the accuracy will be.
What's n again? What's n again?
And
So,
the number of times.
Yeah, big N is the number of times you
Oh,
apply this failure. So in the end, it's the number of quantum samples you're using, the number of times you're using these original orbitals. And so what we find is that if we choose this n to be 1 over epsilon, which is something we already knew from before, if we choose n to be 1 over epsilon, we are going to get an epsilon approximation over expectation value.
Sorry, you said something about the derivative. Is it like calculating the derivative at some point, or
Yeah,
is it more
so-
general, or?
So in general, indeed, if you like replace this g of this g of e of x by like f of g, then also for like non-linear functions of f, functions that are a little bit more wonky, then you can use this technique to kind of estimate the gradient of a function at a particular point.
And take a fixed point to have beforehand, or?
Yeah, so you need at some point to have like some access to f like in intermediate phase.
Oh, okay, okay.
So the gradient estimation algorithm I was referring to is an algorithm that takes a phase oracle of a particular function and outputs like the gradient, and it does this, or at least it uses this idea like with some tweaks. But here we are in a very simple setting because the function that we're considering is exactly linear, so therefore we don't have to. Okay, so what we've done here is we've basically like, taken the original univariate algorithm, but kind of like tweaked it with some of these oracle conversion techniques and arrived at the same result. So like nothing like really special we've done so far, but we've kind of like rephrased it in a new way and also really modified it. Like it's not going to be like the same circuit. If you implement this, there's really going to be some differences in the implementation. Any questions before we go to the
Maybe the small n here that you take for your discretization of the grid, it's linked to, like, it will be specified later, or we just take a
So okay, so in the end, what you take for like the small n is not going to come back in like how many times you need to call the base oracle. So in general, the only thing you need to care about is that you use like a sufficient number of points in your grid, such that like the resulting outcome will also be sufficiently precise. Like the more points you take in your grid, the more kind of like space you have in your outcome. So I can say that even more specifically, the more fine-grained you take the points in your grid, the higher the bigger the range the outcome can be. Because like the Fourier transform always has like this kind of inverse effect that however more precise you take your grid, the bigger the range of your outcome can be. So if you take like a twice as fine-grained grid, you can have outcomes that are twice as big basically, but not like more precise, but just twice as big. So you need to make sure that you have enough points that like the bounds exceed whatever like n times e of x can ever be.
Yeah, but then doesn't it like influences the choice of n as 1 over epsilon? Like,
No, so typically,
be careful about what we are doing.
yeah. So typically you choose n first, the capital
Okay,
N,
okay.
and then you choose the little n in such a way that it is.
Okay, so that okay.
And then typically like the little n will be like log of capital N.
Okay.
Yeah, and in the end, like the little n is like the number of qubits you use.
Yeah, that's
implement your quantum.
This is similar to the classical space complexity, or the classical space with none of the log overhead.
That's a good question. I haven't thought about this so much, honestly. I guess classically, you can just, you would have to store the log d number of different runs of like the one-dimensional algorithm. So you
In
would
the
have
multivariate case, right?
yeah, okay. So in the univariate case, you wouldn't need to do that indeed. So you would only have,
Description of,
yeah, you would have to have two registers, I guess, with like this binary description. So you need really little. So here, yes, you would need a little bit more, and then like this little n, which is kind of like the size of it. And then with whatever else you need in order to then implement this, which has like also like some logarithmic number of qubits. I mean, there's a little bit of like polylogarithmic overhead being hidden here. That kind of, will be more than whatever you need in the very simple classical.
so is overhead is space or is it
Also,
oracle?
it's going to be query complexity as well as space complexity. And also,
And time.
Yeah.
Okay.
yeah. So like this tilde here is hiding like quite some log factors. Yes. Yeah. So then, now of course it's kind of like the point that we have been leading up to. So now we know like how we can do like the univariate case, and now let's see what kind of these ideas we can use in order to do the multivariate case. So in the multivariate case, let us first consider this very peculiar setting. Like after we will try and kind of do things in order to make this less peculiar, but let's first focus on this very peculiar setting to get like the simple picture. So let's consider that our random variable takes values in kind of like the what is it, the octant or whatever, like the quadrant where everything is positive, all the entries are positive, and the L1 norms by one. So we are kind of like in this, how do you say, polylope. And we're also going to take like a grid again, but this time we're going to take a grid that's kind of like, also d-dimensional, and that again has this weird thing that you are using 0 but 1. And then what we're going to be doing is we're going to define this function f in much the same way as what we did before, but now instead of taking the product, we take the inner product between vectors from our grid and the expectation value. Right, because our expectation value is now also a vector, so you can take inner product. And now what I'm claiming is that you can again implement like a probability oracle to this function f, which I wrote down here, which is basically like the exact same lines of expressions as we had in the previous slide, but now with a couple of vectors and transpose. And if you look here, you can see why we need this requirement that we are bounded in a one norm, because we want this expression to be bounded by 1. Otherwise, it's not like a valid amplitude, and we cannot use it in the quantum state. So this is where the requirement of being bounded in a one norm comes from. And we can do the same thing as we did in the previous slide. We can take a probability oracle and turn it into a phase oracle. And then the next step also is like the same as what we did in the previous slide, because also in d dimensions there's a quantum Fourier transform that has like much the same properties, and differs from the one-dimensional case in the exact same way that it takes inner products in the exponent. So we can use the exact same trick by starting with like uniform superposition over all points in our grid, then applying n times this phase oracle, and then running the inverse quantum Fourier transform in order to get an an estimate of our expectation vector. And finally, again, what we get is that the number of quantum samples you're using is going to be 1 over epsilon. So kind of we get the analogous result from the univariate case in the multivariate setting by modifying like the univariate algorithm, and then observing that you can use the same ideas in the multivariate.
And this is with any D?
Yeah, this is for any D, yes. So there will be some like logarithmic overhead here in D itself. So there will be some log D, but like the crucial thing here is that we obtain this 1 over epsilon, whereas classically you would have the 1 over epsilon squared complexity.
So your space complexity, scales with D, right?
Yeah,
Obviously.
certainly.
So will your time complexity?
Yeah, also because you need to implement the inverse conocrator form, which is already.
Yes. So in terms of time complexity, you don't win with like compared to the trivial case where you individually estimate each of the components.
I don't think so. No. Yeah, no, I don't think. So it's really like, sample complexity that is kind of like the thing that we're winning, or like, how do you say, gaining something. Any more questions? So then, okay, so like this is nice. We have like an algorithm that kind of gives us what we want, like the same quadratic improvement that we also have in the univariate case. But we have this very weird assumption on the domain on the range of our random variable, right? We have that it has to be bounded in this very weird region. Like, it's not clear why this at all would be kind of desirable. So it makes sense to kind of take this idea and see how far we can push it, how big the domain is that, or sorry, the range is that we can use, and still retain like these results. So let's have a look at improvements that you can do over the approach that we just had. So the first idea is that if you take one of these phase oracles and you run it in reverse, so you just take its whole implementation, take the whole circuit and flip it, run it in reverse, then what you end up doing is implementing the reverse operation, which is adding a negative phase. So we can, in some sense, handle negative values as well, but we have to kind of, first do all the positive parts and then all the negative parts. And if you do this, then you can extend your range towards not having only positive entries, but like also allowing for negative ones everywhere. Right. So there's like some subtleties here, but not so many. So like this is really like all the ideas you need. Then there's like a next modification that we can do to our algorithm, which is like taking our grid and moving it such that the center is around 0, and also removing the fact that it's bad for people with OCD. So we can take this grid G and put it in the center, and then we can observe that this inner product that we had in our expressions in this probability oracle that we were building, that this inner product will in almost all of the points in our grid be bounded by the L2 norm of the vector that we are taking the inner product with. So it's kind of like a Markov inequality argument that all the points in our grid will have a not so large overhead, like a not so large inner product with any given sample from the L2 ball. So with this idea, we can kind of extend the L1 ball argument to the L2 ball argument and still retain the same scale. Then another thing we can do is, if we're not after like the expectation value vector itself, but we are after some kind of rotated version of this expectation vector, then what you can do is you can take this grid and kind of rotate it the other way, and then apply the exact same algorithm, and you get an expectation of an estimate of the rotated version. Just like small tweak you can do. And then finally, what you can do is, if you don't say that kind of like your random variable is like exactly bounded by some ball, but you only claim that like the majority of the probability distribution is somehow bounded by some ball, So equivalently saying that somehow the trace of your covariance matrix of your random variable is bounded, then you can still apply these techniques. And this is in the end the result of I presented in QIP. So and kind of the high level idea is to take this bounded covariance matrix random variable and find exactly where we have kind of like L2 balls where the majority of the probability distribution is located in it. So we try to find quantiles, we try to find circles where we can show that a large portion of the probability distribution is inside. And once we have done that, we are basically back in the bounded setting, and then we can use the ideas from earlier. So in some sense, we take this bounded variance case and reduce it to the completely bounded. Right, and the core idea here is that all of these improvements retain this 1/epsilon scale. So there's not really any hope that you can, in these settings do anything better. Like 1/epsilon, it's a very small argument to show that 1/epsilon is the best you can hope for in these settings. Any questions about this?
Could you maybe probably you said this, but I don't completely get why you need this L1 norm or the restriction on the previous slide.
The L1.
Yeah.
Here. So here we're going to take like this inner product between a point in our grid and a point in the range of our random variable. And we want that this inner product is bounded by 1 because otherwise we cannot encode it as an absolute.
And you want it to be non-negative as well, just for.
Yeah, because like if we take the square root of a negative number, it's also going to be weird. So this is something like we have to take into account. So and because like the points in our grid are from some kind of L infinity cube, we need to have some kind of L1 bound on the range.
On the exact same.
Yeah.
Maybe it's silly, but like if we had a larger than one norm, couldn't we just add more stuff to the garbage and still compute on one what interests us? By dividing it by its norm, and, making this usual trick here. Like, why can't it?
Yeah. So you mean replacing this one by like? Yes. You can always scale the problem and then.
Yeah. Yes. Okay.
So that would show up in your epsilon, no?
Yeah, true. Yes. So if you assume that your bound is, I don't know, L or something, then the number of calls you need in order to obtain the same precision will also be L times it.
Yeah. Okay. Good. But okay, another question. The number of samples, like the total number of samples you have to do with the d-dimensional mean estimation, like in the quantum case, if I understood correctly, it's like all tilde of 1/epsilon.
Yeah.
Yeah. But it's because the samples are already doing it on D stuff at the same time.
Yeah. Yes.
But like, so if we are a little bit cheeky and like, because the size of the actual quantum memory here, how does it scale with D concretely?
The quantum memory, or like the number of qubits used.
Yeah, the number of qubits.
So indeed, the number of qubits used will be linear indeed because we need to write down.
Yes. So in fact, if we just count the number of samples of one stuff, actually you're making more. Like if we count D times each sample, each quantum sample, you're actually making more samples with this method than the classical case.
No, because the classical case also needs to write down the D entries. No.
Yeah, in memory, but like in time complexity, here you are making 1/epsilon samples of size D, basically.
Yeah.
While in the classical case, you're making 1/epsilon squared samples, but and you do that log D times, okay?
Yeah, but the samples itself will also be size D, no? Because one sample will also be like D-dimensional.
Yeah.
But there is a number of samples. In your case, what it is?
1/epsilon.
Example you mentioned is time D.
This is about the query, or.
Yeah, not in query complexity. The query here is 1 over epsilon.
The number of sample.
Yeah, but with the definition it shows for samples, which is basically when you take a
When you
sample
go
of the
back to the
whole,
original one, when you change the definition of.
Oh, yeah, like what I was discussing just now is if you change the definition of samples, to take into account the number of parts in the memory that you actually sample with the gate, like the size of the gate as well. I was not so sure about the
So
improvement.
here,
Yeah, so indeed, like the operation itself that samples, that writes down the whole binary description of your d-dimensional vector that is your sample. This operation itself indeed will have like most likely some linear overhead in the so the argument that I would make is that this is similarly the case in the classical setting too, because also classically you need to write down these d entries.
Yeah. So you still get the log d on top of the 1 over.
Yeah, I mean there will be log d things here too. So like so the gain is really like in the polynomial dependent on
But you don't lose any stuff.
yeah.
Logarithmic.
Yeah, indeed, you lose some polylogarithmic things. Yeah. Any more questions?
you have more slides or?
I have.
I have a question, but I'm not sure if I end the end of the talk or if I do it now.
Well, I have one more slide with like content and then some.
Okay, so I can ask a question also. It's in this Chebyshev inequality, there is also the variance, and everything you did for the one dimension can go to the Chebyshev case, and then we can play with the variance. So is there an analogy here? Maybe it's related to the covariance matrix, meaning maybe it means what happens when the covariance is not bounded, for instance. What can you do?
Covariance is not bound.
Yeah. In the Chebyshev is also is also the same thing. You do something when the variance is not bounded. So I don't know if it's related. I don't know if you have...
So if the variance is not bounded, then certainly your random variable is also not bounded.
Yeah.
So then like you are what you call in a heavy tail distribution, in which case any of these like classical sampling methods will also not kind of converge nicely. Therefore, like you recover the same behavior as what you have in the classical setting, that somehow taking samples is not going to give you anything
You
meaningful.
can deal with that classically, right? Like that, what didn't you have seen like ESA paper?
But even classically, we can do something. So
Heavy tailed.
you do what you have to do, and you know the number of sample is depend of the variance over the expectation. Basically.
Right.
But I don't know. Maybe you don't address this in your paper.
No, so
then it's another.
yeah, I guess indeed what you're going to get is that like somehow taking samples and taking the average is not going to be like something that will work. So you would have to do something else. And then I would think that also quantumly you would maybe have to do something else.
I was wondering if this covariance bound is it related to the variance bound? So I don't know.
Yeah. So like the trace of the covariance matrix is like some of the diagonal elements, and on the diagonal you have the variance of the margin.
Okay.
So it's a sum of the margin of the street.
So probably here, when you say you relax, it's also when the variable is not bounded, but the covariance bounded.
Is bounded.
Okay, so then what remains maybe to do is what happens when the covariance is not bounded.
Sure.
Okay.
Yeah. Okay. So then there's one thing that's kind of like still kind of left hanging in the air, which is like that in the classical setting, we could handle the case where kind of our range was bounded by some square, our range was bounded in L infinity. Whereas in the quantum case, we now have an algorithm that works whenever we have a bounded L2 moment. So maybe like, is there something interesting going on in the case where we relax this even further and only require that our samples are bounded in L infinity, which is bigger than required that they're bounded in L2. And so, can we maybe also get this 1 over epsilon also in like the same case where you have like the classical 1 over epsilon squared dependence? It turns out that this is not the case. So let me talk about limits. So now, like, we did a lot of tweaks to our algorithm to make it more and more powerful. And in this final slide, I will show that this is where it stops. So there's not really anything more. So, okay, so we saw the L1 case, and we saw that classically you can get like a 1 over epsilon square complexity, and quantumly you get 1 over epsilon. And we also saw that you could, like, port all of these ideas, go to the L2 case and get like the same behavior. And we know classically that you can, in the infinity case even, get the 1 over epsilon squared. But we were able to show that quantumly, you can either do like the classical thing, or do like all of the trickery that I just described, but then you will get an extra factor of square. And this is necessary. This is not something you can.
This is for estimation in infinity norm.
Yeah, this is for estimation in infinity.
Does it change if you?
So if you want a different algorithm, then you take all of these expressions and multiply them by d to the power 1. So if you want, instead of an L infinity norm estimate, you want an L1 norm estimate of your expectation here, then you just multiply all of these expressions by a linear factor.
How do you go from like the right picture is L2, right? Sorry, it's L1. So why do you multiply it by square root d then?
No, so there's two things, right? There's a bound on the what your random variable outcomes can be. These can be bounded in some norm.
Yeah.
And there's a bound on how close you want to be to your true mean in what norm you want that.
Oh yeah,
So-
the people were in L infinity, so it didn't show it.
Yeah, exactly. So before we were only talking about getting an L infinity estimate of your mean, because we had like this small hedged cube in one of the earlier slides. If you'd now changed like the shape of that hedged region to be like an L1 region, then all the complexities change in this perspective.
Is there any intuition for this square root d lower bound?
Yes. Yeah, well, I mean, so there is a lower bound proof, and if you look at the proof, what it does is the following thing, that in a lower bound proof, what you're usually doing is you're kind of looking for a set of instances that's somehow hard to distinguish from one another. And in all of these cases, so in this case and in this case, all of these hard instances are quite simple instances that have either samples that are all very much on the edge, or sorry, in the corner, or here, like you have like samples that are computational basis vectors, and you use these because these are somehow like the furthest away from the origin. So they are like the furthest away from one another. And the same carries over to the L2 case, but then once you go past the L2 case, you can kind of rotate all of these hard instances to be diagonal, and then you can extend them further. So somehow like the pattern breaks whenever you exceed across the L2. Yes, okay, maybe this is a bit too vague, but somehow the fact that you go from L1 to L2, your hard instances are somehow like the standard basis vectors, and then when you're at L2, you can kind of rotate the whole picture, and then when you go from L2 to infinity, you use like the diagonal things as the hardest instances. So this is kind of like quantitatively what happens in the lower bound argument that changes. Okay, yeah, I cannot talk. I can tell you more about this, but then I would have to kind of spend some more time, I suppose. Any more questions? Okay, then then what I can do is just summarize what we've seen. So we looked first at these oracle conversion techniques. These were really like the black box results that we needed in order to give all of the results in the stock. Then we looked at how we could take like this univariate mean estimation algorithm, turn it into a multivariate one. Then we had like a list of ideas that we could kind of like use as improvements over our algorithm. And then we had a look at the limits of this approach. And in terms of where to go from here, well, there's a lot of things that you could still try to investigate, even though we have limits. So one thing is obviously the log factors that already came up a little bit. If you really want to like nail down log factors as well, it is probably also necessary to have a very close look at these black box results from like the 2018 paper. So like this is really like you know, a big thing that would like take many steps in order to try and do. So like this is, you know, if you want like a big project, then you can try this. Another thing you can do is like, so in the previous slide I showed like these 3 bounded settings, and then also had this claim about like other LP norm estimates. So one thing that's still open is if you have the covariance matrix bound and then want LP estimates. This is something that probably has a similar argument that like would just have to be figured out. So this is a rather small question that you could try and tackle. Then one thing that's interesting about the original univariate algorithm is that instead of giving you like only an additive error on your expectation value, it actually gives you something more. If your expectation value itself is very close to either 0 or 1, it will give you an estimate that is like closer, that's better. Like if your expectation value itself is like very, very small, it will give you something that's more precise than the additive error epsilon itself. This is something we lose in this approach. So like this particular like property is something we don't retain, and I'm not sure whether it's possible to kind of modify it such that this is also retained or something. I don't know. Like, could very well be that you cannot do this, but that's something that would be interesting to figure out, I think. And then finally, what's interesting is like that all these classical methods, they all give you like an unbiased estimator for your expectation value. And this is also something we lose. Like the methods introduced here somehow introduce some bias in the resulting estimate for the expectation value. So it would also be nice to try and see if like all of these methods can somehow be modified in such a way that you also retain unbiased in the whole procedure.
Does this already show up in the Oracle conversion?
Yeah. I guess yes, because there's a little error already in this conversion that happens.
Would it maybe be possible with randomization techniques to get the bias away?
So that's something I'm looking into with Gilyén.
So we've looked at quantum phase estimation. It seems if you change slightly, if you give a random basis, because on average your bias is 0. Depending on where you are, on average your base
Yeah,
is 0.
exactly.
So
Yeah.
Yeah.
So this is indeed something we would, but like so this would remove the bias in like some of like the subroutines, but then if you want to generalize, you would have tried to see if this idea itself is flexible enough to kind of like carry over all the way to the high level results. So yeah, I think this is very nice research direction to explore. Yeah. Okay. Well, then I guess it's time for me to finish the presentation. I guess we already had many.
Can I just ask one question? Could you, I'm curious about this 18 result, like what it's a hard conversion, like it's a hard algorithm to convert these oracles?
Yeah, it uses these quantum singular value transformation techniques. Which, so like they are also like in the construction there are these existence results. Like you have to find some polynomial and then you have to kind of decompose it and you can show that this is possible because it contains roots, but you need to first find them. So like there's a lot of like machinery going into this conversion technique. So like one thing that would already be very nice, I think, is to try to kind of find an easier proof of that it's possible.
Seems elementary, right?
But yeah, but that proof would be is not super clear to me. I also didn't think about it too much, I must say. Any more questions?
Maybe if there are more questions, you guys are also still around.
Sure. Yeah.